The title of our paper is Towards a MEMS-Based Adaptive LIDAR, and the project is a collaboration between NEC Labs America, Washington University in St. Louis, and the University of Florida. Light detection and ranging, also known as LIDAR, is an active sensing-based approach to measure the depth of a point in a scene. Over the past decade, this technology has improved dramatically and has thus begun to play an important role in a range of domains, including augmented reality and autonomous navigation. All of that said, conventional LiDAR sensors have a range of limitations. Namely, they're expensive, they're constrained mechanically in resolution, and they're heavy both in terms of payload and power consumption. Our goal for this project was to design an adaptive LiDAR that addresses some of these limitations. The backbone of our adaptive LiDAR design is a MEMS mirror, which we can control using a MEMS mirror controller. The controller allows us to change the angle of the MEMS mirror so as to change the direction of the edge diode. This allows us to control where in the scene we want to foveate our LiDAR point source to. When the light from the edge diode returns from the scene, it will be captured by a single detector, which is adjacent to the MEMS mirror controller. Lastly, we also co-locate a color camera with our LiDAR system. This enables us to get a different modality of the scene, which can be used for depth completion or to control the direction of the MEMS mirror. Please see the paper to learn about how we optimize our design's field of view, volume, and receive radiance, and how our design compares to other potential designs. For our adaptive LiDAR prototype, we used an SF30C laser rangefinder that has a range of 100 meters and a Miracle MEMS mirror as our adaptive mirror. Here we show our adaptive LiDAR prototype that we built using these two devices and a range of other components. In addition to building a LiDAR prototype, we also trained a deep depth completion neural network to upsample our sparse LiDAR depth samples to create a dense depth map. Finally, we conclude this presentation with some results from our adaptive LiDAR sensor. We show both adaptive sampling and depth completion using our prototype. Here we show results from our adaptive LiDAR prototype. The first row shows images from the co-located RGB camera. The second row shows samples from our LiDAR prototype, and the third row shows outputs from our dense depth completion network. We will now look at some real-time adaptive LiDAR sampling results. On the left, we can see the samples from our LiDAR, and you can see that the field of view of the LiDAR is changing depending on the position of the hand. This is because we are adaptively changing the mirror so as to only sample regions of interest. In this case, that would be the hand. On the right side, we show the depth completion output from our neural network that takes as input the samples from the left-hand side.